Now is start into chapter 9, and chapter 9 is where we go back and we're going to actually look at what Newton said. So Newton, far as we're concerned, gave us his first law, his second law, his third law, and even his law of gravity and his Principia, and he did. But if you actually look at the text, what you will find is that in the Principia, his second law, Newton's second law of motion, was not F equals ma. In fact, it's this. So I'm going to go ahead and share my screen. And it's probably going to make, yep, it made me download again because it's a new week, I guess. So I'm going to share my screen with you guys. Okay. And I'm going to tell you what it actually said. So what Newton's law said, and I always write the left-hand side, which is the sum of all the forces, basically. I usually write it with the big sigma. And that's because I want you guys to remember it's not a particular force is equal to M times A. It's the total external force acting on whatever you consider the system to be. And the system has a mass M, and that will result in an acceleration A given by F equals ma. That's the version of Newton's second law we've been looking at. So just to remind you of that, I'll say that this is the net external force. Now, what do I mean by net? That means you're going to add up all the forces acting on the system. And what do I mean by external? That means you can't pull yourself up by your bootstraps. In other words, you only count the forces that other objects are putting on the system, not forces that one part of the system is putting on itself. So that's the left-hand side. But here's the part that he actually said. What he said was the instantaneous rate of change of momentum is equal to the net force. And we define momentum P is defined to be mv. So you can see if you put in mv there, m times dv dt, which is what ma is, that happens to be a special case in which the mass is a constant. So if m equals a constant, and I mean a constant in time, then the summation of the forces is equal to d by dt of mv, which equals m times dv dt, which equals ma. So that is the version that we've been using, but in fact, that's a special case that happens to only work in the case of m being a constant. In fact, this version at the top is the real Newton's second law. Okay, so this momentum, as you can see, is a vector quantity. I'm going to say oops, I did not mean to do that. Is equal to momentum. So that's how you spell it. And in fact, I'll also allow you to realize that P is a vector quantity and its units are kilograms times meters per second. Okay. Now, in some cases, you can basically realize that the summation of the forces on average is essentially equal to delta P over delta, over delta T. So a lot of what you can do is, for instance, this type of calculation, which is doing an average. So let me show you an example. So a typical tennis player, at least when the 4th edition of the textbook was written, a typical male tennis player would hit a serve at 120 miles per hour, which is about 55 meters per second. That's pretty darn fast. Now, given the time from then to now, I can now tell you that modern male on the tennis circuit playing, for instance, in Wimbledon or the US Open, the Australian Open, or the French Open, is often hitting 135, 140, 150, 157, something like that. I think the highest or the world record right now is over 160. And females are often hitting like 120, and Serena Williams, before she retired, was, for instance, occasionally would hit 137. So that's a little bit dated, but what I'm going to tell you is that when you hit a tennis ball, it's pretty reasonable to assume that the initial velocity of the tennis ball is 0, and that the final velocity is, let's actually go ahead and say 60.0 meters per second. That'll give us a little bit more of a buffer and put it closer to reality. 55 meters per second is about 120 miles per hour, whereas 60 is a little bit better. So I'm going to do that. And I happen to know that the mass of a tennis ball is about 0.060 kilograms. And the big deal here is basically that the time of contact, delta T, is on the order of a millisecond. I really wished I would have reminded myself of that before I started class, because that's actually a useful amount of time to have. I'm actually looking it up real quick. 0.0, so 5 milliseconds is about the right answer. So delta T is around 5.0 times 10 to the negative third seconds. In other words, about 5 milliseconds. So what I'd like to do is say, what is the average force? And notice I put just the average symbol up there instead of vector, because though this is a vector equation, I'm treating everything like it's moving in one dimension. So I'm imagining a ball sitting perfectly still, a tennis racket coming through, hitting it for about 5 milliseconds, and going in a straight line at that process, and then the ball taking off at some new speed, 60 meters per second. And in that small period of time, the acceleration of gravity is not going to have any real major effect. So it's not going to deviate from a straight line. So I can pretend this thing is just moving along the x-axis. So the fact that it's a vector just means that we use positive if it's going one way and negative if it's going the other. So with that in mind, I can say that the average force is about equal to delta P over delta T. And remember, the delta always means final minus initial. So this is P final minus P initial over delta T. And that's just the ugliest P I've ever written in the world. But anyways, it's mass times velocity. So I'll go ahead and factor out the mass out front. I'm going to say 0.060 kilograms times V final is going to be 60.0 meters per second minus V initial, which is 0 meters per second. And then divide all that by 5.0 times 10 to the negative 3 seconds. And I think you can see the units are going to work out to kilograms, meters per second. And then you're going to divide that by second. So you get kilograms, meters per second, which is in fact exactly equal to a Newton. So 0.060 times 60 is 3.6. And now I'm going to divide that by 5e to the negative 3. And that gives me 720. So the force is about 720 newtons. Now, that's about 180 pounds. So yeah, swinging a tennis racket, you're going to have to develop a pretty large force to actually hit a serve at 130 miles per hour. So it's going to be about 180 pounds. That's a pretty big deal. I mean, that's a big enough force to lift a fairly heavy person, not your instructor, because I happen to weigh quite a bit more than that. But that is a pretty significant weight. And that's all applied to a small tennis ball whose mass is about 0.06 kilograms. Any questions on that? And it turns out that is the change in momentum. It's got its own name. There's a quantity called impulse, and that's what it is. So I'll take a break again from this and reiterate from the summation. Oh, actually, I should have put that vector symbol up there. The summation of forces is equal to dp dt. I can manipulate that a little bit and say that delta p, which is equal to the integral of dp from p initial to p final, okay, that's also equal to the integral of the net force times dt. And this quantity is called the impulse. So notice there's a couple ways you can calculate it. You can do P final minus P initial, that's the impulse. Or you can do the integral of the net force over time. That is also the impulse. Both are perfectly acceptable. And usually you'll have enough information to do one version or the other, but not both. Okay. And what I want you to understand is if you, for instance, wish to be an athlete, and let's say you want to be a professional baseball player or a professional women's soccer player or professional women's softball player or basketball, whatever, all of these things, well, most of these things, basketball not so much, require you to be able to hit something with as much force as possible so that you can hit the ball at a higher speed. In the case of baseball and softball, you can hit it at a higher speed, or you can finesse it in a very specific direction so that you can, hit it between fielders or something like that. But a home run is generally considered to be a good thing. So hitting one over the fence is a good thing in baseball and softball. Fast pitch or slow pitch doesn't matter, just until you get into weird rules like there's one-up rules and stuff like that. But the main thing is you're taking a ball that might be coming towards you at, say, 100 miles per hour, if we're talking about fast pitch baseball, and it's going in one direction at 100 miles per hour. Your ideal scenario is to send that same object back in the opposite direction or close to the opposite direction, going ideally even faster than it was thrown at you. So hopefully 140 or 150 miles per hour or something like that. That means your mass times the final velocity, which would be in, say, the positive direction, minus the mass of the ball. And I said your, but I mean the ball, minus the mass of the ball times the initial velocity, which is in the negative direction. So that minus a minus gives you a plus. That delta P being MV final minus MV initial, you want that to be very large. So the impulse is the thing you want to be very large if you want to hit a home run. And you can look at this conceptually and say, okay, well, there's a couple ways I can do that. Pretty much I can inject testosterone into my bloodstream, and that will make my force get bigger. So that's one way you can do it. you can use the old tried and true method of working out, and that will make your muscles stronger, and that can make the force larger. You can also change techniques. You can learn how to, for instance, there's a video that you could buy. A friend of mine bought it when we were playing competitive softball, and it was basically a how-to video of how to hit a softball 400 feet. So in that case, they showed you this really weird way where if you're batting right-handed, you take your left hand and literally only have one or maybe two fingers on the nub of the bat. And then outside of that, you have maybe one or two fingers of the other hand on the just above the other finger, so that the bat is now basically about a half a hand's width further out from your center of rotation. So that's one way to make it get bigger, and it's causing the bat swing to make a faster bat, and higher bat speed means higher force and therefore a higher impulse. So there's a lot of ways you can do it. But what you see is that right-hand side there is an integral of F as a function of time. So you want to integrate the force as a function of time. And that might look something like a graph like this. Here's T, here's F, right? Now, the wider that you integrate this over, right? You're going to integrate the total force over a time dt from T1 to T2. So you see that if you have a very narrow amount of time, you're not going to get that good of a hit because the F delta T integral is going to be very small. But if you go from here to here, you'll get more hit. Here to here, you'll get more hit. This is why we have sayings like hit through the ball, or swing level. And they have a very specific interpretation that I'll give you some ways of thinking about it that might help you a little bit. So for instance, if you consistently just swing your bat level, meaning perfectly horizontal, you're not necessarily going to hit it very well. Okay. If, however, you see that a ball is coming to you, say, from this rightmost ball to this leftmost ball, then that sort of defines a plane in which the ball is coming. Now, if you swing your bat in that same plane, then what you're going to find out is that that is a way you can interpret swinging level. You are swinging your bat head on the same plane as the ball is coming to you, at least at its most recent look. Okay. When you do that, what happens is the center of mass of the bat and the center of mass of the ball, obviously 2 points make a line, but with that in mind, then the contact point is dead center between them and you get a solid hit. So that's one way of thinking about it. Not only that, by swinging in the same plane, you actually stay in contact longer and give it a little left-right spin, for instance. But the main thing is that you're in contact longer. So this integral over time will be a larger quantity, and therefore you'll get a larger hit. Okay. So that's some of the details of batting and concepts of physics that help you understand. Like, if you go out to a tennis court on any given day, you'll see a newbie out there, a new person learning how to play tennis, and they've probably either heard or seen people using topspin, and you'll see them and they'll just literally swing the racket straight up. That doesn't work. Okay. You literally have no forward momentum with the actual tennis racket. So you can't impart a forward momentum with the ball. You can barely do it just because of the inertia of the tennis racket, but that's about it. So hopefully, even if you're not that athletically inclined, you'll immediately know that that is not a good swinging method. In fact, what you want to do is swing through and then brush up towards the end. That can give you the top spin. And if we were covering fluid dynamics, we would cover the Bernoulli principle and how to get spin on it, including curveballs and sliders and top spin and bottom spin and all that good stuff. But we're not covering that. If you have an interest in it, let me know. Maybe I can do an extra segment about it. But the main thing is, that's what we learned about momentum. Now, something else interesting about momentum is this. Newton's second law says specifically that the summation, actually I should do this in black, that the summation of the forces, in other words, the net external force, is equal to dp dt. But if the summation of the forces is equal to 0, then you get something kind of interesting. You get dp dt is equal to 0. What kind of a function has a derivative equal to 0?
A constant.
Exactly, a constant. So if you have a p equals a constant, and this of course is a vector equation, so that means a constant vector. So p equals a constant is what occurs if the net force is 0. And what this means is momentum is conserved. Because it says p is a constant. So if you're looking at, for instance, two balls rolling towards each other on a pool table, okay, you can calculate the momentum of the left ball and the momentum of the right ball by taking the mass of the left ball, which should be about the same as the mass of the other ball, but you're going to take that mass and multiply it by the velocity of the ball. And of course, you can say, for instance, the x-axis is right down the middle of the pool table, and then you can take a cosine of the angle and find the x component of the velocity, and take the sine of the angle and find the y component of the velocity, and multiply that by the mass. And then you have mass times x component I hat plus mass times y component j hat for the left ball. And then you do the same thing for the right ball. And what you have is the total momentum is, of course, those two summed together. So the mass of the left ball times the x component I hat plus the mass of the right ball times the y component of velocity j hat plus the mass of the right ball velocity in the x direction I hat plus the mass of the right ball velocity in the y direction j hat. That's the total momentum before the collision, but the total momentum is a constant. That's what Newton's second law says when the net force is 0. So it's going to be a constant. So after they collide, you now have a new direction for the velocity of the left ball and a new direction for the velocity of the right ball and a new magnitude of the velocity of the left ball and the velocity of the right ball. So you do the same stuff again, taking cosines and sines to get x and y components. And the part that you get after the collision, that's going to have to be true too. Okay. In other words, the sum of those vectorially should be equal to the sum of those vectorially before the collision. That's what conservation of momentum is. Now, it doesn't always have to be truly that the net force is 0. For instance, when two cars collide, there might be friction forces acting on the tires and the metal and stuff like that while the vehicles are colliding. And if that happens, then obviously there's a force in it. But if that force is really small compared to the, hundreds or thousands of newtons that are crushing one car against another, in that case, you could probably ignore the force that's being added by friction. In other cases, you can't. So it doesn't always have to be truly 100% zero forces or 100% zero total force acting on the system. It could be very small forces compared to very large forces, and the small forces are irrelevant and the big forces cancel out. So because the big forces, by the way, if you're treating the system to be the two cars, then the big force that car one is putting on car two is an internal force and never would be on the left-hand side of Newton's second law anyway. Any questions on that? Okay, so it turns out that that's not the only type of collision that can occur. There's also another type of collision called an elastic collision. And in an elastic collision, that means that kinetic energy is conserved. Okay, that's not a thing that normally happens. Kinetic energy is quite often wasted. You can tell, for instance, like if you walked up and touched a piece of metal on a car right after a wreck, you would find the metal on the car is quite a bit hotter than it would have been just before the collision. That's because some of the energy went into crumbling the car, and in crumbling the car, you heated it up. You can see that if you take like a paper clip and bend it and bend it back and forth a bunch of times, the actual paper clip will get hot. So if 20 times it got, after 20 times it got hot enough for you to feel it, you can imagine maybe it got 1/20th of hot by one time. So that's sort of the approximation that you're making. But yeah, by deforming metal, you've lost some energy in the heat. So kinetic energy clearly would not be conserved because that's a form of energy. And the whole energy you had was kinetic energy of one car plus kinetic energy of the other car. But in an elastic collision, which is closely, if you're looking for macroscopic large objects in everyday life that might be elastic or might participate in elastic collisions, you don't want to think about small spongy balls. You actually want to think about really rigid steel balls or pool balls, for instance. They're pretty close. You can tell they're not 100% elastic because as soon as they hit, you hear them. So clearly, sound, you probably know, is a wave, and waves are things that carry energy from one place to another. Therefore, the fact that you heard the sound tells you some of the energy is being lost. So some kinetic energy must be lost in that scenario, but you're going to get a small fraction of it lost when the balls that are hitting are actually quite rigid. So pool balls are very rigid, steel balls are very rigid. Or if you go at the microscopic level, there's really no smaller objects that can participate that could steal energy. So most of those collisions can be elastic anyways. So just keep that word in mind. If someone says it's elastic, that means something. So let's look at, for example, a one-dimensional head-on elastic collision. Okay, so conservation of momentum, which I'll write as MC, momentum conservation. Okay, well, what we're looking at here is we're imagining an object A moving with velocity VA and an object B moving with velocity VB. And then there's a collision and object A is now moving with velocity VA prime and object B is moving with velocity VB prime. Okay, if that's the case, then what we have is MA, actually, yes. Did somebody ask me a question? Okay, it looks like they didn't. All right, so that's the total momentum of the system before the collision. And then after the collision, MA VA prime plus MB VB prime. This is the equation for conservation of momentum. Kinetic energy conservation, KC, is going to be this equation, 1/2 MA VA squared plus 1/2 MB VB squared is equal to 1/2 MA VA prime squared plus 1/2 MB VB prime squared. Okay. So that's what conservation of kinetic energy looks like. Now, here's a neat trick. What I'm going to do is I'm going to manipulate equation 1 in a neat way that I know gives me some results. So equation 1 is going to give me MA times parenthesis VA minus VA prime. And then I'm going to get MB by itself on the right-hand side. And when I do that, what I get is VB prime minus VB. Okay, so I'll call this equation 1 prime. Now I'm going to do something similar to equation 2. So what I'm going to do is, for starters, I'm going to cancel out all the 1/2s because clearly I can, right? And why keep them? But now what I can do is I can say MA times VA squared minus VA prime squared is equal to MB times VB prime squared minus VB. Okay, that's pretty good, but in fact, I can do it better. If you recall, there is something called a difference of squares that factors quite nicely. So I'm going to go back to black. I accidentally did not mean to write that in black, in red anyways. So now I'm going to write this.
VB supposed to be squared as well?
Yes, thank you for catching that. Yeah, I just completely left it off because I was realizing that I had written it in red and wanted to correct it. So yes, now I'm going back to writing in black. I'm going to write this as VA minus VA prime times VA plus VA prime. And then this will be MB times VB prime minus VB times VB prime plus VB. And this is going to be what I call equation 2 prime. Now I'm going to divide 2 prime by 1 prime. And of course, you can see already that the MA times VA minus VA prime is going to cancel out. And what I will get is, in fact, just VA plus VA prime on the left-hand side. And what I'm going to get on the right-hand side, again, the MB is going to cancel out and the VB prime minus VB is going to cancel out. So all I have left in this case is VB prime plus VB, which you can group up a little better by doing the initial, in other words, the unprimes difference equal to the primes. And when you do that, you get VA minus VB. That's the difference in the initial velocity of A and the initial velocity of B. It's sort of the relative velocity of A to B. And then on the other side, what you have left is, in fact, VB. In fact, actually, let me not do that. Let me do a parenthesis, and then I'll put VA prime, or excuse me, yeah, VA prime minus VB prime. Okay. All I have to do to make that the case is put a minus in there, and this will in fact be equation 3. You can use equation 1 on your equation sheet, you can use equation 2 on your equation sheet, and you can use equation 3 on your equation sheet. So I'll put little stars by them. Okay, so this is a really valuable result, but notice it's very specific. It's for a 1D head-on elastic collision. I'm going to do a couple problems with this in a second, but first I'm going to take a simple problem and solve it in one dimension without using all those expressions, even though I could use them. It's just more complicated to use them than to not. So let's imagine, for instance, that we have a train car. So here's a train car. And let's say this train car is moving with a velocity of VA is equal to 5.00 meters per second and has a mass of, let's say, 12,000 kilograms is equal to MA. And then sitting still over here is a empty train car that's not moving, and MB is in fact 1,000 kilograms. Okay. Now they are going to collide and stick together. So they act as if it's one big object whose mass is 13,000 kilograms, which we know is actually MA plus MB. Okay. And what I'd like to find is V prime equals question mark. Now, this is a train car riding on a train track and another train car sitting still on a train track. They stick together after the collision. That's called a perfectly inelastic collision. It's also called totally inelastic, various things you can use, collision. But the main thing is when they stick together, it's called perfectly inelastic. And you realize already that elastic means kinetic energy is conserved. So you might think, why is this called inelastic or perfectly inelastic or totally inelastic? The reason why is if you jump to the center of mass frame, which is the frame in which the total momentum is 0. So in this case, well, this case would be hard to figure out just on my head because they have different masses. But if you move to some frame where the momentum of the left car was exactly the same in magnitude as the momentum of the right car, but opposite in sign, then the total momentum would be 0. And then when they collide and stick together, that means they're going to sit perfectly still. And that means the total kinetic energy is 0. So that's why they use that terminology, because the kinetic energy will be 0 after the collision. But it's a weird thing to do all that. So anyways, I just gave you that. So you'll know that sort of that's a maximal decrease in kinetic energy. So let's go ahead and compute, assuming that this is the total force acting on these two train cars system is 0. Okay. Now there's obviously some friction acting between the train track and the train cars, but that's probably pretty small compared to the weight of the train car and the normal force, which actually just cancels it out. And then the force that the two cars have for each other, that's an internal force, so it doesn't matter. So conserving, or actually I'll write it, solution. momentum conservation gives me the following. I'm going to say 12,000 kilograms times 5.00 meters per second plus 0, well, the velocity of the first one, 0, is equal to 13,000 kilograms times v prime. Okay. So I can solve for v prime. That's going to be 5 times 12 is 60. And that's kilograms meters per second. And then I'm going to divide that by 13,000 kilograms. So
I got 4.6.
okay, let's check. Yes, I got 4.62 on that one myself. So that equals 4.6. I'll give you one extra sig fig, 4.62 meters per second. Notice how the kilograms did cancel out. So that's the new velocity. Well, the reason why that new velocity is so big is the initial train car was really, really heavy and moving along pretty well. The second train car is on the order of less than 10% of the mass of the first train car. So yeah, it had very little effect. That is one way we could go about determining the final velocity. Now, something you might also want to know is, well, now that we know the final velocity, what's the change in kinetic energy? So I'm going to go ahead and do that and say delta K. Well, actually, so that was part A. And part B, delta K equals question mark. Well, delta, like I've told you guys several times, delta always means final minus initial. So this is K final minus K initial. Well, the K final is going to be 1/2 of 13,000 kilograms times 4.62 meters per second squared minus, now remember the other one had two things and they were separate, but one of them had a velocity of 0. So I don't need to count it because that's going to be 1/2 times 1,000 times 0 squared. So this one's just going to become 1/2 times 12,000 times 5.00 meters per second squared, like that. And when I do that, I'm going to first get 0.5 times 13,000 times 4.62 squared. That gives me about 138,000. 738 or 739, way more sig figs than I really have. And that unit is joules minus 0.5 times 12,000 times 5 squared. That gives me 150,000 joules. When I subtract those two, I get negative 11.3 times 10 to the third joules is the change in kinetic energy. Okay. As you can tell, I didn't do anything. I just, used conservation of momentum, but that alone told us kinetic energy was not conserved. In fact, kinetic energy was very much lost. And that's normally the scenario. You're going to lose some kinetic energy in a collision. Any questions on that problem? All right. So let's look for a second at let's say, pool balls in a one-dimensional head-on collision. Well, I was going to write pool, and then I changed it last second to write billiards. All right. Consider two identical pool balls with initial velocities. What are their V finals? Part A. If VB is equal to 0. And then part B, if VB does not equal 0. Okay, so I have those results, and I have basically equation 1. So let's write this as, I'll do this one blue this time, solution. We can say that the net force on the pool ball should be about 0. That means we're sort of ignoring the potential spin and stuff like that. And that's not too bad of a estimation, but with that in mind, number 1 gives us MA VA plus MB VB is equal to MA VA prime plus MB VB prime. But here's the kicker. MA equals MB is equal to M. So we can cancel out all the M's, and we're just going to get, in fact, VA plus VB is equal to VA prime plus VB prime. Okay, we haven't even considered whether it's elastic or not, but now I'm going to say assume elastic. Okay, the reason why I mentioned that to you, that we haven't even touched elastic yet, is I want you to realize you can use that one equation there even when it's not elastic, because that's just conservation of momentum, and conservation of momentum occurs whenever the net force acting on the system is 0, or when the net force acting on the system is really, really small compared to the other forces. Okay, so we've got this expression. Let's call this 1 prime. We also have that VA minus VB is equal to the negative of VB prime minus VA prime, right? That was equation 2. So what I'm going to do is I'm going to add 1 prime and 2. When I do that, notice the VB and the negative VB on the left-hand side cancel out. So I get 2 VA on the left-hand side. However, on the right-hand side, I get a negative VB prime with a positive VB prime. So those two cancel out. And then I get a VA prime plus, because a negative times a negative is plus, VA prime. So this gives me 2 VA prime. So what I've now learned is that VA prime, which was an unknown, is actually equal to VA. So that's one solution. In other words, what can happen is VA, the first particle, say A, could run into B and basically collide and then have the exact same, at least magnitude of velocity as it did before the collision. Now plugging this in, which by the way, I'm going to call this equation 3. So 3 into, let's say 2 gives me 3 into 2 is going to give me VA minus VB is equal to negative VB prime plus, now VA prime, I'm just going to write VA here. You can now see that I can subtract VA from both sides. And lo and behold, what I get is that VB prime, which is something we wanted to know, is in fact equal to VB. So you could imagine this as basically the two particles completely missing each other. That's one way of looking at it. Or they could bounce off of each other and have exactly the same magnitudes and go the opposite way. Okay, so that way would work as well. But that's a scenario of what could happen. Now, this is all for part A. Actually, this is all for part B because part A was where I said VB is equal to 0. So yeah, I should really call that part B. Now let's see what happens when I do part A, where VB is equal to 0. Well, that means 1' is now going to be equal to VA is equal to VA prime plus VB prime. And equation 2 gives us that VA is going to equal negative VB prime plus VA prime. Okay, so all I did was took those two equations and substitute VB equal to 0. I'm going to add them again. And that's going to give me 2VA is equal to 2VA prime. So again, we get VA is equal to VA prime, or VA prime is equal to VA. And now I can also plug this back in to say equation 1. Or 1 prime. And that's going to give me VA is equal to VA plus VB prime. That gives me VB prime is equal to 0. So in this case, we definitely have basically the scenario where it missed. So that's some of the stuff you can do, for instance, with using these equations. You can also solve it when the masses are not the same. And that gets a little more complicated, but it's definitely doable. So let's look at another example. What I want to do this time is I want to consider different masses in a 1D head-on collision. So again, I've got equation 1, which is MAVA plus MB VB is equal to MAVA prime plus MB VB prime. I've got 2 which is equivalent to MA VA squared plus MB VB squared is equal to MA VA prime squared plus MB VB prime squared. And then I've also got VA minus VB is equal to the negative of VA prime minus VB prime, like that. That's equation 3. So we can use these again as we wish.
Professor Younger, don't you need 1/2 in equation 2?
I did, but I remember I showed you where it canceled out. So I went ahead and just canceled that out already.
Okay.
Yeah, so you can see where I did that there on line 1 on this one. Oh, excuse me, it wasn't there. It was the previous page. Maybe it wasn't. Maybe it was there. Nope. Oh, maybe 2 pages back. Yeah, there it is. So I did it where on line where it says equation 2. Because there's a common factor of 1/2, you can just basically divide through by 1/2, and that gets rid of all of them. But yes, in principle, if you are asked for the kinetic energy equation, yeah, you better have those 1/2s there. I'm at the point where I'm just trying to figure out what I'm going to do with each one. So what I now am considering is 2 objects, and ultimately what I'm going to consider is A, what is VA prime and VB prime, and then B, if VA, or excuse me, if MA is much, much greater than MB, then VA prime equals question mark and VB prime equals question mark. And then part C, if MA is much, much less than MB, then VA prime equals question mark and VB prime equals question mark. That's the big thing that I'm trying to figure out here. So I'm going to take equation 3, solution. From equation 3, I'm going to write this as VA minus VB is equal to VB prime minus VA prime, and I'm going to solve it for VA prime. And of course, that's going to give me VA prime is equal to, if I pull it over to the other side, it'll be VB prime plus VB minus VA. Now I'm going to plug that into, I'm going to call this equation 4, and I'm going to plug 4 into 1. When I do that, I'm going to get MAVA plus MBVB is equal to MA times, now I'm going to put in VB prime plus VB minus VA, and then plus MB VB prime. Now remember, I'm pretending I know MA, MB, and VA and VB. The only things I don't know are VA prime and VB prime. So I've now eliminated VA prime, and this allows me to actually solve for VB prime. So what I'm going to do is try to get all the VB primes together and everything else on the other side. So I'm going to say MA VA plus MB VB, and now I am going to pull MA times VB. I'm going to pull that to the left-hand side. That's going to become minus MA VB. That takes care of this term. And minus MA VA will become positive MA VA. over to the left-hand side. So that takes care of that term. And then all I've got is MA plus MB times VB prime left on the right-hand side. So I can see that I've got 2 MA VA on the left-hand side. And then I've got plus VB times MB minus MA on the left-hand side. That takes care of that term and that term for the 2 MAVA. And then that takes care of that term and that term with the VB term. And this is all equal to MA plus MB times VB prime. So finally, I can solve for VB prime by saying it is in, whoa, everything just erased. By saying VB prime is in fact 2 MA VA over MA plus MB. And of course, that is times VA. And then plus MB minus MA over MA plus MB. All that will be times VB. So I've now gotten a general expression for VB prime in terms of VA and VB. Any questions on that? Now, if we were to take VB equals 0, then you just get this, this expression right here. And that's kind of nice because that looks a lot like the tension in the Atwood machine. Uh-oh, running out of time. That's actually pretty nice expression because it looks like the tension from the Atwood machine. And what you'll find out is another equation that comes up when you're solving this looks like the acceleration from the Atwood machine. So it's actually a pretty astute and helpful observation. So now I can say, okay, let's take this part right here. And this is VB prime if VB is equal to 0. And in fact, this part right here, MB minus MA over MA plus MB, that looks like the actual acceleration from the Atwood machine. Now that I have VB prime, I can actually use that to find MA prime. All I have to do is say, let's lasso this baby. Copy. Flip over to here. Paste. Okay, so now I have that equation over here, so I don't have to recopy it and evidently picked up extra B somewhere. Now, I also had used, what did I, oh, this part right here, I'd used VA prime from here. So what I'm going to do now is I am going to, again, lasso this stuff. I'm going to copy that and paste it right here. So now I know what that is. So I can now say that VA prime, whoa, we're using blue, so I'll go back to blue. Whoa. So I'm going to say, going back to the blue and getting rid of this extra B here. VA prime is actually supposed to be VB prime, which is what we got here. So that's 2MA. I think I copied an extra VA on that. Yes, I did. All that trouble was for nothing in making that thing there. Yeah, I wrote the VA twice, so that's what happened there. Sorry about that, everybody. Anyways, we're going to, of course, ignore it. Let's see up here on this one. Okay, so it's 2MA over MA plus MB times VA plus MB minus MA over MA plus MB times VB. Now that's just the VB term. So I've gotten that, which actually I have to multiply that by 2. So I'll put a 2 right here because I didn't realize that that was VB. Well, I wonder if that was a miscopy. Was that supposed to be VB prime twice, or was that supposed to be VB? Yeah, that was definitely supposed to be VB prime plus VB. So that was an error there. Luckily, I corrected it on the other thing. So anyways, that was this little guy right here was not supposed to be there. That little prime signal symbol. And actually, we're out of time anyways, so I will leave this up to you. You can see these are exactly the examples that your book worked to. I've just done explained some of the algebra to you, so you should be able to do it now. I will in fact leave this part more or less undone because I need to check and see, because I had this little symbol, this prime symbol on here, that might have led me to make an error in getting that last expression. So I need to check that to make sure. So I'm gonna basically leave this be, but I'll check and see if there's a problem that arises in this expression for VB prime as a result of me having an extra prime there. I will let you know via notes or whatever if I find one. But you guys are free to go. Don't forget what I told you about the midterm. I'm going to go ahead and try to turn the midterm back on so you guys can see it. I'm doing it right now. So everybody is, of course, free to go. And I'll wait here till the last person leaves in case anybody has any questions.
You mind showing the other pages, please?
Yes, the other page, that one.
Actually, all of them.
Oh, all of them. Okay. That's the first one. Just tell me when you're ready to switch to the second one.
Go ahead. Go ahead.
Okay.
Go ahead, sir.
Okay. I have now switched the hide correct answers to hide it on 11:59 p.m. March 21st.
Go ahead. Go ahead.
There you go. And I'm doing the same thing for the testing center one because I know I had 2 students, I think 2 or 3 students took it at the testing center.
I'm good.
Okay. Thank you, sir.
Thank you. I have a question about the final. The final exam is gonna be from chapter 8 to the rest, or is gonna be from chapter 1?
I usually make it comprehensive, which would mean from chapter 1 all the way through every chapter we've covered. Sometimes it might not include the very last chapter, but generally it always covers everything.
Okay.
Professor, I got a question for you.
Yes.
I sent you an email this morning. I was supposed to take test 4 yesterday, but something came up. But I know that you usually say in your syllabus that it takes about 48 hours for you to respond.
Yeah, I
was
just
wondering-
made it available, so you can now take it. And in fact, I did the same thing for people that might have missed test 3. So test 3 and test 4 are now available until Friday.
Okay, Okay, thank
And
you.
if you didn't get it on time, then of course it's going to be like a 5-point deduction. But other than that, you're good to go.
understandable. Okay, thank you.
All right, you're welcome. All right, I've now changed so that you can see the final exam that you took. You can see it with the correct answers up until tomorrow at 11:59. I would probably check that immediately just to make sure it's working so you can get a hold of me if it doesn't. But other than that, you're free to go. Anybody else have any questions?
I'm gonna check that one, let you know.
Okay. I'm looking at this right now to see if there's any errors in there. It looks like I copied it correctly. Yeah, I did it correctly in the line where it says plug 4 into 1. I actually put that in correctly, VB prime plus VB. It's just for some
Okay.
reason I did not do it correctly right there. So I'm going to take this little thing and get away with it. Okay, you go away. So this all worked okay. Yep.
So physics 241. Oh,
Now, I can actually try to use that. Let's see if that actually works now. So that's not 2 times this.
practice term. Midterm.
I'll get rid of that.
Oh, mine open, but I don't see the click here to view the results. Yeah,
You're looking at your midterm right now.
yeah, it doesn't do anything.
It
just-
should ask you for your lockdown browser. If it's not, that might be part of the problem.
Or it has to, oh, okay, you still have to go through the lockdown. All right, all right.
Yeah, I have been
Then
told, various students told me that that was the case for that.
Okay, then I'll do later then.
Okay, no problem.
All right, bye-bye.
Bye-bye. Anyone else? Grace, do you have anything?
Yes, hello. Jessica and I apologize for not being in class today. We had a sudden engagement.
Okay.
Also, we were wondering the information regarding the midterm that you had during class.
Okay, so what I told my students is I've made the midterm available now via correction until tomorrow at 11:59 p.m. You can actually go in and look at all the questions from the midterm as well as all the answers. Plus, it will let you know which one's the correct answer. You want to get a copy of that unless you're completely content with your midterm grade. You want to get all those either written down or take screenshots or whatever, because I'm giving you the opportunity to do the entire midterm over again, not just the ones you missed. You got to do the whole thing. And you can turn it in to me by a week from Wednesday. And if you get that turned in, then let's say you get 50% of them right. If you got 50% of them right, I'm going to give you 50% of some number of points added to your midterm grade. If you get 100%, I'm going to give you 100% of that number of points. And that number of points depends on how well you did. So for instance, if you're one of my students that got between, let's say, a 40 and a 20, then maybe I'm going to add 20 points to it. So if you got 50%, you're only going to get 10 of those. If you got 100%, then you're going to get 20 of those. But I'm going to have different ranges based on what your initial score was. That's going to bring your midterm up immediately. But not only that, at the end of the semester, if you do better on your final exam than you did on your midterm, then I will replace your midterm grade with your final exam grade.
Okay. And So this is still, and we go into the lockdown and we do, so we have to take, like, put the codes you had.
No, you shouldn't have to put any code. You should be able to click right on your score, and that
Mhm.
should take you right into the test. It might ask you to open up your lockdown browser, but other than that, it should go straight to the test.
Okay, all right.
Let me
Thank you.
know if it doesn't work, or talk to another student just in case maybe they know something about how to do it that I don't know, which is a very likely and realistic possibility. But yeah, try that.
Okay. All right, thank you.
You're welcome.
Bye.